And yeah, I just want to say this is we're going to be spending maybe 2 1/3 lectures today talking about P equals 2 for the Brumer star conjecture. This project was definitely a beast to complete, and I think you'll see that with all the different little twists and turns we have to take. I think this is, this project was probably, the most difficult project and rewarding in some sense project that I've been a part of. So I thank my collaborators for that. Um, I'll try to say like what's fundamentally wrong, difficult. The most fundamental thing that's difficult is the proof of Ribot's lemma, and Julia will be devoting her entire lecture to that, and I'll spend a portion of my last lecture also talking about that. Okay, so I like this part 1, 2, 3 that Pierre had in his slides. So one thing I like to do at conferences is, steal ideas on making slides from other people. So this is from Pierre. Okay, so part 1 is Ritter-Weiss modules. Okay, so recall that we had this Ritter-Weiss module, which Mahesh described in quite a bit of detail, but maybe one of the most important things about it is just that it sits in a short exact sequence like this, where XSH is the group of degree 0 divisors on the places of H that lie above S, which I denote by SH. And then sort of the main theorem that, so I should be careful, I should say this theorem isn't exactly proven in our Brumer star conjecture, but this is kind of the main result that we're going to, is this conjecture of Burns, Gruhauer, and Sano, which we show implies the Brumer star conjecture, because it implies essentially that theta annihilates the class group. So theta annihilates this because it's in the fitting ideal. And then, okay, so this isn't quite the class group you want, but it's pretty close. But you can see theta annihilates this because it's a subgroup of something it annihilates. But yeah, you need to work a little bit harder to get, you want to get rid of this S. That's a little bit more difficult. But anyways, Mahesh explained how to prove this theorem for P odd in the special case where S equals S infinity. Okay, and it's a little bit, of work, or say a little bit, it's a lot of work to go from what we actually prove in the general case when S doesn't equal S infinity to this statement. And so, Christian has a very beautiful paper that's out now that explains one method of doing that, and we have a sort of a different approach that I'll talk about in the afternoon. Okay, so there are 3. So this part 1, part 2, part 3 that's going to happen today has to do with 3. How I break down the main aspects of why P equals 2 is different into 3 parts. So the first part has to do with the Ritter-Weiss modules, and on the analytic side, you see something that's different going on at P equals 2 because the constant term of the Weisstein-Eisenstein series is theta divided by 2 to the n. And so Mahesh's work, we kind of ignore this 2 to the n because it's a unit, right? So we don't care about it. But you see it when you're working at 2. And so to explain this power of 2, you need to do some modification on the algebraic side so the Ritter-Weiss module sees theta, not theta over 2 to the n. So what's going on, right? So you need something algebraic that sees the 2 to the n. And the 2 to the n is coming from the infinite primes. And so what you really want to do is you want to remove the infinite primes from S. And so just as a notational framework, we assume that S union T contains S infinity, but we no longer assume that S contains S infinity. So that's kind of like the perspective change that we make when we go into the new paper on P equals 2, which is we allow ourselves to move infinite primes from S to T. Okay? And so we define a Ritter-Weiss module more generally in this setting where you move primes from S to T, infinite primes, and then the adjustment of the statement is that the fitting ideal of nabla is theta divided by 2 to the T, where T is the number of primes you've moved from S to T. So if you move all of them, then you get exactly what you want. Okay, but there's a warning, which is that it's unfortunately essential in the construction to assume that S is not equal to the empty set. At some point, if you remember the details of Mahesh's construction, we have, when you want to prove that nabla has a quadratic presentation, you have this module which you called B, which is basically the kernel from a bunch of product of Z bracket G's to Z bracket G, but somehow if you want to split that and say that that's isomorphic to just a bunch of copies of Z bracket G, but you can't do that if S is empty. So that's kind of a problem. So and we don't know how to prove, or it's probably not true that you have a quadratic presentation if S is empty. So S is empty is basically a situation that you have to avoid. You're not going to get a principal fitting ideal, so you're not going to be able to prove a statement like I made in the previous slide if S is empty. Okay, and so Mahesh, for simplification notational purposes in his talks, took S equal to S infinity, but I can tell you more specific in the general case how we actually modify. He said we in the general case need to modify the sets S and T. He kind of swept that under the rug in his talk by just assuming that S equals S infinity. But what you need to do is a similar kind of moving. You move all the ramified primes that are not in A, that are not above P into T from the S set. So that's kind of the trick that even in our first paper with Mahesh on the Piod case, that Mahesh spoke about on the Piod case, we did this trick where we, instead of taking S to be S infinity union all the ramified primes, we took S to be S infinity union the ramified primes that are above P. And all the other ramified primes we put into T. And now I'm saying, furthermore, move all the infinite primes into P. So we're moving as much stuff into T as we can. Okay. But now the problem is now this S might be empty, right? So this is an issue, not just, right. So this is an issue, not just if S is unramified, but actually if it's unramified outside P, this would cause us an issue in our paper, which is, most extensions you probably would be unramified out P. They'd be interested in Brumer Stark. So you would have a huge condition that you don't want to have if you had to deal with it, if you had to, avoid that case. So you really need to figure out how to avoid S being empty. And so we do the simplest possible thing, which is we introduce an auxiliary prime and we just stick it in to S. Okay. But now everything is modified at that prime L. So your theta function is modified, your modular forms are modified, and then we're going to see the biggest issue where this causes a problem. So a lot of it goes through. The biggest place where it causes a problem is in the study of the Gauss representation. So that's what I'm going to kind of focus on a little bit later. But let me just go back and say, so part 2 will be a discussion of the Gauss representations at this prime L that you've put in the case when S would otherwise be empty. So, but let me just say what happens with the modification at the infinite primes, how you modify it when you move the infinite prime from S to T. So the basic idea is, if you remember the details of Mahesh's, you have this local complex mapping to the global complex, and the component in the local complex at an infinite place that was in S was just in from GW to G of HW. This is the completion at the place above, your place of S, which we call W, of just the completion. So in our case, where F is a totally real field and H is a CM field, this HW is just C. Okay, so the idea, and this is really due to my former postdoc Jesse Silliman, is to we had C star. That's what I should have said. Sorry, in Mahesh's construction, C star, and his idea is to replace it with C, and this kind of maps to this by the exponential map. Okay, so previously this is an exact sequence that Mahesh had of OHST star mapping to these free modules B and B. This sort of gives the quadratic presentation of Nabla. Okay, but now we have to sort of update this with our new definition of V, and we get something which we just call UHST in the paper, which is some kind of extension of OHST star, basically by copies of 2 pi I Z. Okay, this group, I haven't written the short exact sequence, but it maps to OHST star by projection onto the second coordinate, and the kernel is basically a sum of 2i pi z's. So we get kind of tuples, x, w, and y, where the y is just an OHST star. That's what you had before. But the xw is kind of a choice of a logarithm. So it's an element whose exponential is equal to y. And of course, there's an ambiguity of 2 pi I z in there. So that's why you get that extension that I get. So that's kind of the short exact sequence that you get. And then you have to kind of redo what we did, where you kind of replace this exact sequence. So I'm saying short. This is not literally a short exact sequence, even though it's an exact sequence and it's short. Sorry. So, but yeah, you have to replace this exact sequence with this one in your work, and you have to, you have to prove this equality. Okay, so I'm not going to say much more about that, other than what I wrote on the slide. But I'll just say that a huge part of the difficulty is the proof. One thing that Mahesh mentioned is that in order to prove the equality, it suffices to prove an inclusion. And that boils down to the analytic class number formula. At the end of the day, that's the input that allows you to show that this inclusion implies this equality. And again, you use that, but the proof is much more difficult. So the proof that's used in the case for P odd to go from here to here is much more difficult. It involves chasing powers of 2, but that's not the only reason it's more difficult. It's actually a fundamentally different proof. The proof in the P odd case doesn't work, and the proof in the P even case, P equals 2 case doesn't work for P odd case. So it's a kind of a completely different proof, but the inclusion implies the equality, and it's much more difficult and was much more hairy to find.
Is nabla still quadratically presented?
Yes, as long as S is not empty.
Even with the modification. Right?
Yes. Yep, even this modification. So it's quadratically, and that's one of the big reasons why you need to assume S is not empty, because otherwise it's not quadratically presented. But yeah, as long as S is not empty, assuming that S union T contains all the infinite primes and all the ramified primes, right? You still have to assume that S union T contains all the ramified primes, but it does in our notational framework.
It's important to get a principal fitting ideal.
Absolutely. Otherwise, there'd be no. Yeah, I mean, you would not have a hope of proving this if you're not going to have a principal fitting ideal, right? So yeah, it's important, and you need the quadratic presentation. You shouldn't expect to prove a principal fitting ideal without having a quadratic presentation.
Samit, to make sure, the inclusion is difficult, or is it the class number formula that's
No. Well, I mean, the inclusion is all the hard work with the modular forms, the Ribit's lemma. But what I'm saying in this slide is just going from the inclusion to the equality is also difficult, right? The proof of that going from here to here, this implication is more difficult, right? It's not as difficult as proving the inclusion itself. That involves a lot more machinery with modular forms and Gauss representations and whatnot. But I'm just saying that it's not so simple as to say, oh, apply the class number formula, right? As it sometimes may see, like in Weil's paper on the main conjecture, where he says that the inclusion implies the equality. It's kind of like just said very in a few lines that, oh, we have this, the sum of the multiplicities of the zeros, we know the sum of the zeros is equal, so therefore you have, right? So, but it's kind of in this context where you're working over groupings, it's very hairy somehow. Like proving inequalities of deals of a group ring is very complicated. Yeah. Questions? Okay, part 2 is the Gauss stage. So the second part that becomes difficult, other than modifying, nabla, giving the modified definition of nabla and proving its functorial properties. So we have to prove a cohomological interpretation of that, as we did in the P-odd case, and then proving that the inclusion implies inequality. So all of that. The next part is the Gauss representation. So let me explain why. And this gets to a very insightful question that Jan asked yesterday. So I'll hopefully address that because I promised I would. So, okay, adding the auxiliary prime L to the set causes difficulties in the modular forms argument. So in the original argument, the only finite primes P and S lie above rational P, and we consider only P ordinary forms. So the Hecke algebra is generated by good operators together with the operators UP. Okay, so by good operators, I mean not dividing anything of interest. So not dividing the level, not dividing P, right? And your forms are eigenforms for those Hecke operators. So sort of the Hecke algebra of a particular form then, well, it's just the field for those operators, because each Hecke operator maps to a constant in the field, the Hecke eigenvalue. So your Hecke algebra would be reduced, it'd be a field. Okay, now you throw in this UPs, but you're asking for you're asking for a form to be P ordinary, and I guess it's a result of theta, but it's not hard to see that it's reduced when you throw in in weight greater than 1, when you throw in a UP eigenform. And the reason for that again is because it's an eigenform for UP, and this has to do with the fact that in your weight greater than 1, there's only one P stabilization that's ordinary, right? Or at most 1. And if it's ordinary, then there's exactly 1. And so again, your UP eigenvalue is just a number in the field. In fact, it's a unit. It's a p-adic unit in that field. And so again, your Hecke algebra for that particular one form is just a copy of the field. And so the total ring of fractions of the Hecke algebra of sort of all the forms is just a product of these fields, and so it's reduced. Okay. But now if you start looking at primes dividing the level and Heck operators at primes dividing the level, you don't necessarily get Heck eigenvalues anymore, right? Especially if you have a prime L that does not divide P. So if you have an old form, the Heck algebra might not be reduced, and I'll say a lot more detail about this in a moment. All right, so I just kind of alluded to all this. The total ring of fractions of Heck algebra has the form the product of Kf as F ranges over all that. So we localize at that, the Eisenstein ideal, so the maximal ideal. So you only retain forms that are Eisenstein. That is, your Eisenstein series is like E of psi comma 1. So the Heck eigenvalues of psi q plus norm of q to the k minus 1. So you only retain forms whose qth Heck eigenvalue is congruent modulo the maximal ideal. This is the uniformizer of the finite extension of QP generated by the Fourier coefficients of F. So if its Fourier coefficient, this is basically modulo P essentially, is congruent mod P to the Eisenstein series, right? Then those are the forms that are retained. Okay, and Kf is the total ring of fractions, kind of the Heck algebra of F, meaning you take the Heck orbit of F and you look at the action of the Heck algebra on that orbit, then you get some ring. Okay, so I said, in the case where your Heck operators are only good operators, and this is just the field, it's just the field E to begin with. But now it's those good Heck operators together with UL, and so you have to kind of study the action of UL on this space. Okay, so the form F is an eigenform for all the good Heck. So I already said this. For all the good Heck operators, so the ring generated by these operators is just the field. All right, and if F is new at L, then the same is true with the UL eigenform with some eigenvalue, and so UL just generates a scalar, and so you're just still getting the same field. Okay, so that's nothing new. But the interesting case is F is old as L, is old at L. Then Kf is, okay, E generated by the action of UL. And as I think Jan said this in his talk yesterday, or someone did, that UL satisfies basically the Heck polynomial of the form of the old form with, L not in the level. Okay, so this is the Heck eigen, the Heck polynomial at L, right? So there's a quadratic polynomial. Now, what happens to quadratic polynomials over fields? Three things happen. You can get a quadratic extension of E. You can get, right? So that's if the polynomial is irreducible. It factors into distinct linear factors. You get E cross E. And then the hairy case is when it factors as a square, and then you get this ring of dual numbers. So that's the problem, right? If you take E bracket X modulo X minus alpha squared, then that's isomorphic to this. Okay, and this is kind of hairy to think about. In this case, you have to do some work also when you're not a field. Okay, but we can kind of handle all three cases together. So what is it that we need, right? So why do we need this Heck algebra? What do we need? What is the input that we take? We need this Galois representation, right? So we need a Galois representation, and we took it into the total ring of fractions, GL2, the total ring of fractions of the overall Heck algebra, which was the product of the Heck algebras of each individual form. So, right, that Galois representation was just the product of the Galois representations of the individual forms. So we need for each form a Galois representation like this. And when this was just the field E, this was just the usual Galois representation we inputted as a black box from the work of Deline and all the mathematicians who work went into that, Carriol and Hida and Wiles and Taylor. So the existence of these Galois representations over a field. But now this Kf is no longer a field. It could be E cross E. It could be the ring of dual numbers. We need to make sure we have a Galois representation that satisfies these properties. So what are the properties that we need? We need that for each prime not dividing the level, right? Or the primes of P or the primes in S that right, this or the primes in S only has to do in this new case where this might have an auxiliary L that we've thrown in. That rho F is unramified, and the characteristic polynomial is this, the usual thing. And for all the primes in S, this is what we use to get the connection between the module that we produce from the Galois representation and nabla. We need to show satisfy certain local properties. And local properties is very familiar from those who've thought about ordinary Gauss representations. We need to know that that the restriction of the decomposition group has an invariant line, and that the quotient eta is unramified and sends a Frobenius et al. To UL. Okay. And now UL is living in this ring, which might be the ring of dual numbers, right? So it's a representation over GL2 of the dual numbers. So we need to know that this exists. Okay. So in the usual case where there's only where the only finite primes in S lie above P, we just take KF equal to E, and this representation is the usual one, right? So that there's nothing to do in that case. In the new case where S is, so I should be set brackets here, where S is just the set of just L, you must construct this row F, and if F has level divisible by L, then by our construction, it turns out to not have level divisible by L squared. Our group ring value modular forms just have L in level, no L squared. So we know each individual form has level L and not L squared. Then again, you just get a field, and you can take row F till this row F tilde to be your usual row F. And the desired local property rho F is a theorem of Carriol. So it's very well known. Oops, let me go back. It's very well known that in the case where you have an ordinary modular form and L is a prime above P, that the Gauss representation has this form. This is kind of very well established in the literature, in papers of Hida. But it turns out that if you're in this case where L is where you have a modular form that's new at L, when L is not divide P, and it's L squared does not divide the level, okay, so the local representation is Steinberg at L, then it turns out that it's known that the local representation has this form, actually. Okay, so that's a theorem of Carriol, and going from, kind of the automorphic language to the classical language that we use was, got some nice help in parsing the literature from David Loeffler and Sugwoo Shin to make sure that we actually had this in that case. Okay, but this is class. I mean, all the experts will tell you, yeah, that's classical. This is due to Carriol. Okay, so what's the old form case? Okay, so it's not super hard, but it just requires an observation. So in the case that F is old at L, we're in a trichotomy, and how are you ever going to produce a new Gauss representation? You're not. So you do the stupid possible thing, which is that you just take the same Gauss representation over KF. Okay, so pretend this is the ring of dual numbers. Now we're in that case. So this argument will work for all three cases in the trichotomy, but just think about the dual numbers case because it's the most interesting. Okay, so it's just you literally take the same Gauss representation. Okay. And now, because it's old at L, the Gauss representation associated to F is unramified at L because L is not in the level. Okay, and so, restricted to inertia, it's just the identity. So all you need to show is that for this one matrix, rho F of sigma L, that it's conjugate over this ring, over this group to this, right? So I said I wanted, a line, and the quotient for Frobenius that L should act as UL. So I show this one matrix is conjugate to a matrix of this form. Okay, and what was UL? UL was the root of this quadratic polynomial. All right, so now it's just a linear algebra lemma, which is let E be a field, A be a matrix with a quadratic minimal polynomial G of X, and let K equal E bracket U modulo G of U for some quadratic polynomial. Then A is conjugate over GL2 of this ring. So this works for all three cases in the trichotomy. It's conjugate over in this ring to a matrix of the form U0 star star. Okay, so I'm not going to prove that for you. That's just linear algebra. That's a little exercise. Okay, but there's a warning here. So we're not done, because in the assumption of the lemma, you need A to have minimal polynomial, this quadratic polynomial, with quadratic minimal polynomial, right? But so this is not characteristic polynomial. This is minimal polynomial, right? So there's a case where the minimal in 2x2 matrices where the minimal polynomial is not the characteristic polynomial. So when you have a scalar matrix, it's the only case, right? When you have a scalar matrix, the minimal polynomial is x minus alpha. If it's a scalar alpha, it's not the characteristic polynomial. Okay, and this proof doesn't work. And of course it doesn't work, because if you have a scalar matrix, you're only ever going to conjugate it to itself. A scalar matrix conjugates to itself, right? So you're never going to get something conjugate to this, right? Okay. So this is relevant only in the third case of our trichotomy. Okay. So how do you deal with the scalar case? And the answer is you can't. You can't deal with the scalar case, so you have to avoid it. Okay. And so there's another lemma, which is that if I have a Hilbert modular eigenform of weight greater than 1, there's a density 1 set of primes. In fact, this will almost never happen that the matrix will be scalar. Okay. And the proof of this, so actually I had a little bit more complicated proof of this because I didn't think of this clever trick of Caligari. So I explained this to Frank, and he said, "Oh, there's actually an easier proof." So the is one line proof. So the projectivization of your Gauss representation has infinite image since the weight is greater than 1. Okay, it's not a finite image representation, and then in the projective representation, saying that it's not scalar, saying that in the projectivization, the image is not trivial. So now it's just Chepitarov. You have an infinite group, and you're only looking to avoid one element. So there's a density 1 set of prime set avoids that. So that's very clever. I had a more complicated argument to show that there exists some L that I mean. So of course this was if this was all primes L, it would be trivial because if all primes L, the Gauss representation was scalar, then of course the whole representation would be into GL1, which it's not. But the point is there's other conditions about L that we need that I'm not telling you. So to prove the existence of, a of a prime L that satisfies other conditions that wasn't scalar, I had some argument, but it's kind of easy to see once you know that density 1 set of primes L are good because the density of the primes that we need to avoid is not 0. So that's okay. So this is that's basically it. So then we put together those Gauss representations and we run through the argument as before. All right. So 2 remarks. So the case that rho f of sigma from L has equal eigenvalues but is non-scalar. So it's like a Jordan block alpha alpha with a 1, right? That conjecturally does not occur actually. But that's the case we can handle because the minimal polynomial of the matrix there is still quadratic. It's x minus alpha squared, not x minus alpha. The case where rho f of sigma is a scalar, that's the case we can't handle, right? Our representation, we can't get a representation of the desired form. But that you can avoid using the Chepitarov argument. So I thought this was kind of curious. The case that conjecturally shouldn't happen, we can handle, but the case that does happen, you can't handle, but you can avoid it. So I don't know. I thought that was very interesting and lucky. And the second remark is that while the argument using so once we input this, I said, okay, then you do your argument. I just kind of said you do it, but you have to go through the argument, make sure it works. And you can modify the argument. It turns out we need to use that each of these local factors at each f, that the maximal ideal is principal. We need to know the maximal ideal, the total ring of fractions over Heck algebra, the maximal ideals are principal. Okay, so we can't handle something like this. E bracket epsilon was like if there's 2 ULs. There's 2 ULs that were old, and you had UL epsilon 1, epsilon 2, you want epsilon squared, epsilon 2 squared. So it's fortunate that S contains at most 1 prime not lying above P. So I just thought I would mention that we wouldn't know how to handle that if we needed to put more than 1. So some generalizations of this argument, this part would get a little bit hairy. So I thought just mention that. All right. So now I want to get to discussion of Ribot's lemma, which is I think the most difficult aspect of the P equals 2, and the kind of, in some sense, the really the fundamental difficulty. The other stuff was technicalities that are important and hard, but not like a fundamental conceptual issue, I think. And Ribot's lemma and P equals 2 is a fundamental conceptual issue. Okay, so here's Ribot again. So I just want to remind you. So what is Ribot's lemma? Let's set the setting. So we wanted to connect, in some form zeta functions to in some form class groups. So in our particular context, it's the Stickelberg element theta, and the version of the class group here is the Ritter-Weiss module, the fitting ideal of the Ritter-Weiss module. So we want to show that the ideal generated by theta is equal to the fitting ideal of Nabla. So how do we connect these two things? We will go around this circle that everyone likes it. It's due. I don't think I mentioned this when I first talked, but this circle is due to Barry Mazer, and he gave a beautiful talk at Ribbit's 60th birthday conference in 2008, and I immediately like wrote this down and printed it into my brain, and now it's part of every talk that I get. So, so if you want to see in print, he had an article in the bulletin of the AMS based on that talk that he gave, which contains this diagram or some version of this diagram. Okay. So, so zeta functions or L functions more generally are constant terms of Eisenstein series. From Eisenstein series, we just define cusp forms. From cusp forms, we make their Galois representations. So we talked about all of this in our talks. And then Rivet's lemma is the way that you go from the Galois representation to the Galois cohomology class. And of course, you need some assumption on your Galois representation to make a cohomology class out of it. You need to have some ideal modulo which the representation is reducible in some sense. So I'll give you a precise statement in a moment, but basically you want to assume that the characteristic polynomials are reducible. And then you want to produce a cohomology class from this reducible sort of modulo I Galois representation. And the Galois cohomology is connected to class groups via Kummer theory, as we've heard in a few of the lectures. Okay, so all right, so here is the version of Rivet's lemma that was in Rivet's original paper. I mean, it wasn't stated like this, but this is the way that, I guess maybe you can express it in the way that it's applied more generally. So Rivet was working over ZP, and so M was basically, P. But basically, if you have a DVR, so let's suppose we're giving a DVR and we have representation from a compact group into GL2 of K. So because K is a DVR, T is a DVR, its fraction field has a topology that comes from the topology of T, and you can ask for, being given a continuous Galois representation and you assume the Galois representation is irreducible, but that it's reducible modulo the maximal ideal. And because the Galois representation is taking values only in the fraction field, what I mean by that is that we assume that the characteristic polynomials live in T. So that's implicit in this statement, saying that's congruent mod M. And implicit in the statement is that it actually lives in T, the characteristic polynomial of any row of G. And that it factors modulo the maximal ideal as the product of two characters, x minus chi1 times x minus chi2. Okay. Then the statement is there exists a non-zero cohomology class in the H1 of G over the residue field T mod M, where I give that residue field an action of multiplication by the character chi2, chi1 inverse modulo M. Okay, so you just take this character into T star and you take it in T mod M star, and then that gives you a character, and you say that G acts on the residue field via that character, and you get a non-zero cohomology class. Okay. So I'm not going to give the proof because Julia is going to give the proof in her talk. Okay, but the basic idea is you can conjugate the matrix such that it lives in GL2T. Okay, and that's because every maximal compact because this is a compact group and it's a continuous map, so the image is compact, and every maximal compact of GL2K is conjugate to GL2T. So you can conjugate your matrix so it lands in GL2T. Then furthermore, using the Brouwer-Nesbitt theorem, you can show that modulo M, now it makes sense to reduce the representation modulo M because it lives in GL2T. You can show that modulo M, it can be basically upper triangular with a chi1 and a chi2, and then you can take the kind of B coordinate, the upper right-hand coordinate, and that gives you a cohomology class. Yeah.
So is it important that the characters land into T star and not just the residue field?
No, I think it's probably fine. And not into T mod M star. Yeah, I have to think about that. Actually, somebody else asked me another thing with that. I think it's probably fine. I mean, obviously, if they could be lifted to characters into T star, then that would be equivalent to what I wrote. So, but somehow, yeah, because if I just had characters, then you would mod M, and you could say that there's some form of the representation that modulo M looks like an extension of chi1 by chi2, but I'm a little worried because you have to change the lattice to get the cohomology class to be non-trivial. And so somehow it's useful if the thing is rigidified so that no matter which lattice you take, you always are getting chi1, chi2. But I have to think about it. And it may very well work. I don't know. Yeah. I like to keep it like this just so that I'm certain that it's correct. But you're right, the statement doesn't require them to be characters in T star, right? This makes sense just having the characters. So that's a good question. I don't know. Okay, so now let me give you another form, which is generalized in two important ways. So one is that we don't assume that T is a DVR anymore. We just assume that it's a reduced complete local Noetherian ring. And we don't assume that the ideal modulo which we have a congruence is just the maximal ideal. So, right, if you're doing Iwasawa theory and you want to have congruence modulo some p-adic L function, some element of lambda, then you want to take I to be sort of, the ideal generated by lambda. So you don't want just congruences mod p, you want congruence mod p squared, mod p cubed, whatever. However divisible the L function is, you want a congruence modulo that, right? So you want to take an arbitrary. So this is already an issue. There's already an issue if even if T is a DVR, if your ideal is not just the maximal ideal. Okay. So now we assume, so what is the setup? We have a topological group G and a representation T bracket G into M2 of K. So now in this generality, I don't want to say that the representation is continuous because K doesn't necessarily have a natural topology that comes from T because it's no longer just a DVR. For example, if T is lambda. Okay, but so I'm going to make an assumption that in number theoretic applications holds in practice, which is that the image of the representation. So you notice I've gone from a group representation to a matrix to an algebra representation, but you can always do that, right? If you have a group representation, you can extend it by linearity from a T algebra representation on the group ring T bracket G to the matrices M2 of K. Okay. So that's how I've written it. So this is kind of, you can take this to be given from a group homomorphism from G to GL2, and then you extend that to an algebra homomorphism, right? And what I want to assume now is that the image of this homomorphism is finally generated over T. Okay. And again, in I'll just say this in words, and this was explained to me by Jackie Lang, that in practical applications, if G is a Galois group, the way that you show this is that there's a condition called the P finiteness condition of Mazur, which says that there's finitely many Homs from G into FP, where FP is the residue field of T. There's finitely many homomorphisms from G into FP. Then you can show that under the assumption that the characteristic polynomials all lie in T, which is another assumption of this theorem, then the representation, the image of the representation is finally generated. Okay. So I mean, the characteristic polynomials lie in T, and the map that takes, an element of G to its characteristic polynomial is continuous. Then that implies that the image will be finally generated. So that's kind of described in work of Belaish and Mazur. All right. So anyways, in practice, this holds. So we're going to assume that. So we assume that, that this map from rho. So now that the image is finally generated, this finally generated module over T has a topology because it's a quotient of finally many copies of T. So we can ask rho to be continuous, and you assume that. And you assume, as I said, that the characteristic polynomials live in T. So this should have said of X, characteristic polynomial of rho G of X. That's a polynomial in X, that quadratic polynomial factors modulo some ideal of T, which I call I, right? So it doesn't have to be the maximal ideal. And assume these two characters satisfy an important condition, which is that chi1 is not going to go into chi2 mod M.
Did you forget to put that in the last slide?
No. I mean, it's not in the last slide, sorry, but it's not because I forgot, it's because it's not needed. So, and it may be the case that you've seen me talk about this before, and I did have it in this case, but that someone pointed out to me that you don't need it in this case. So so it's been removed from this slide from maybe a version of this talk I gave before.
What's been removed?
That you don't need to assume that chi1 is not going to go into chi2 here. So when you're working over the maximal ideal, I mean, the point is that the Brouwer-Nesbit theorem just tells you that the semi-simplification of rho bar is isomorphic to chi1 plus chi2. So you don't need to assume that it's chi1 is not congruent to chi2 in a mod M, because the you sort of get the fact that you could mod M, you can make it an extension of chi1 by chi2 or vice versa. Okay, yeah. So the question was, do you need to assume that chi1 is not going to go into chi2 in this slide where you're working over a DVR with a maximal ideal? And the answer is no. But yeah, so once you generalize, so that's a really good question. Actually, it's an insightful question, because once you generalize to an arbitrary local ring and an arbitrary ideal, and this is what Wiles had to do in this proof of the main conjecture, or I guess already in Maser-Wiles they had to do this. They realized you need the assumption that chi1 is not congruent to chi2 modulo maximal ideal, and so this proof I'm going to explain, because I think it's kind of clarifying to see what the difficulties are when chi1 is congruent to chi2. Now, there's an additional assumption that you need somehow, and this is what Rivet uses to great effect in order to prove that the cohomology class is non-trivial. You need to know that the global representation, when you're not modding out by I, is irreducible, right? So otherwise, if it was reducible, you'd never be able to produce a non-trivial extension class. You could just have a sum of two characters, and there's no extensions there if you just take the sum of two characters. So to make this precise, well, I'm assuming this K, just for the purposes of this talk, I mean of this discussion, I'm assuming K is reduced here. So this capital K is a product of fields. And so if I take a projection onto any one field, I ask that projection is irreducible. It's a representation over a field. Okay. Now I should mention that, yeah, I just got through telling you how you can't deal with just reduced Tekka algebras. You need to deal with the non-reduced case. So there's a generalization of this to the non-reduced case, but for simplicity in this part of the talk, I'm just going to assume everything is reduced. Okay. Then the conclusion is that there exists a fractional ideal of K. So this is what I mean with fractional ideal, sort of a finely generated T module that's sitting inside K, such that when I tensor with K over T, I get all of K. Okay. So fractional ideal and a surjective cohomology class in H1, and it's the same kind of thing. So instead of T mod M, I have to replace T mod M, first of all, by T mod I, because I have a general ideal I now. But moreover, it's not just T mod I, it's B mod IB for some fractional ideal. So that's the kind of generality that you need to allow yourselves, and that's what Maser-Wiles do. And the character, again, is given by chi2, chi1 inverse, so the reduction of these characters modulo I. Okay. Now, what does the word surjective mean? This is non-standard terminology. It's something we introduce. You want to know that the cohomology class is not trivial. Like, what if it's just zero? Okay, that would not be good, right? You want to know that this cohomology class is big. It's this module, right? It's it fills up the module, right? So, for example, if you're working over a field and this was like 7-dimensional, that's saying that you've produced the whole 7-dimensional cohomology space somehow, because, right, if you had if you look at the projection onto the different factors of this, if this was a 7-dimensional vector space, and any of those cohomology, and there's some linear dependence between the projections of those cohomology spaces, then it would live in a subspace of the 7-dimensional space. It wouldn't be the whole space. So you want to know that you're getting as many cohomology classes here. This one class is seeing as many classes as big as this is. So if this is 7-dimensional, what you're saying is I'm proving 7-dimensional space of cohomology classes, right? So you're saying that your cohomology is surjective, means that the image of any representative cocycle is the whole module. Any representative cocycle, not just one representative. Yeah, that's the definition of surjective. Is that any representative cocycle generates this as a T module. Okay. So there's lots of insights of Maser-Wiles. So this is a great, observation on how to generalize Ribot's lemma in this. And one of them is just what the statement should be. And it's that, you should have a surjective cohomology class, right? When you're working on a field, you can say non-zero, right? Non-zero means you generate the field as a vector space over itself. So, but if you have a bigger module, you want to know what it is. So you have a surjective cohomology class, and the real insight is that it's not in T mod I, that it's, you have to generalize to allowing an arbitrary fractional ideal and B mod IB. Okay. All right, so let's prove this. Let's prove this. So what you do is, okay, you start with, you just start the whole proof with the very important residually distinguishable assumption. The chi1 is not congruent to chi2. You take something that realizes that. Okay, so if they're not congruent as characters, it means there's some elements such that they're not congruent. So by Hensel's lemma, this characteristic polynomial, which factors modulo I is x minus chi1 times x minus chi2. Now these are not congruent modulo maximal ideal. So the polynomial has distinct roots modulo maximal ideal. So by Hensel's lemma, you can kind of lift them to roots of in T. T is a complete local ring, so you can lift these roots. And so then you choose the basis to be the eigenvectors associated to these eigenvalues, lambda 1 and lambda 2, that are distinct. So rho of tau looks like this. Okay. All right. So now, once you've chosen this, so this is Wiles's great argument that leads to the definition of pseudo representations. So we know, okay, what's the trace of a matrix? It's A plus D. And what's the trace of, okay, rho of sigma? So this is our special tau now. It's A of sigma tau plus D of sigma tau. Okay. And we said, now we know how to multiply matrices. So if you take tau to be lambda 1, 0, 0, lambda 2, and you multiply it by A, B, C, D, and you see what you get, then the trace of that is just A lambda 1 plus D lambda 2, right? So now we have two things that are in the Hecke algebra, T, and if you multiply the first by lambda 1 and subtract from this one, then you get lambda 1 minus lambda 2 times D is in T. But now we use again that lambda 1 is not congruent to lambda 2 mod M because this was congruent to chi1 and this is congruent to chi2 mod M. This is the unit in my local ring because its difference is not the maximal ideal. So that means that D is in T. Okay, now going back here, if D is in T, that means A is in T. Okay. This is what Wiles observes, that this residually indistinguishable condition gives you that A and D live in the ring T. All right, so that's super important. Now, what about B and C? So it will not be the case that B and C live in T, and you cannot hope to prove that. That's just not true in general. So that's the first departure from the DVR case. The first thing in the DVR case, we kind of explained using the theory of Maxwell compact subgroups that kind of the whole representation can be taken to live in T. And this will no longer be true. Okay, so if turns out the residual representation is irreducible, you can prove this, but the whole point is we're in the reducible case. So you can't prove this. Okay. So this is just a comment. We don't use this in the proof, but notice that B of sigma, C of tau is a difference of A, so it does live in T. So you can kind of package the information of the A, the D, and for every pair, sigma and tau, B of sigma times C of tau, together, consider those triples. That's what's called a pseudo representation. It's just a collection of triples, right, that satisfy the rules under representations that these elements would have to satisfy that come from, matrix multiplication. So I just want to mention that it's very important, but we don't use the perspective of pseudo representations in this talk or in this. Okay, so that's all right. Now, what more can we say about A and D? Okay, so oops, sorry, went too fast there. Extra click. So all right, so again, the trace. So I kind of repeat this argument to give the integrality. So the trace of rho of sigma is A plus D, but now I know that's congruent to chi1 plus chi2. That's kind of what we're assumption of the theorem, that the characteristic polynomial factored modulo I as x minus chi1 times x minus chi2. So the trace is chi1 plus chi2. Now you do the same thing with sigma tau, and you get the same kind of thing before. You get modulo I, you get A times chi1 plus D times chi2, right? And then now it's like I have two variables, A of sigma, D of sigma, and two equations, this one and this one, and you can solve them. And again, you're going to end up inverting chi1 minus chi2 of tau. And what you're going to get is that A is congruent to chi1 and D is congruent to chi2. So that's cool. I have not just that they're integral, but they're congruent to the characters. So the diagonal entries really look like, the matrix was somehow reducible mod I with it, 0 mod I and had a chi1 and a chi2. Okay. And now you just proved that basically works. So let B be the T module generated by the B of sigmas Okay, and so one of my assumptions of the theorem is that B is, oops, it's got cut off. Oh, no, I think it's just on here. A finally generated T submodule of K. And then furthermore, so I'm not going to explain this, but the irreducibility assumption, it does imply that B tensor K is all of K. So in other words, like if B didn't have a component, like have any presence in one of the factors of K, then the Gauss representation would be reducible because you'd have a 0 there, and right. So it's not reducible by assumption. So kind of B sees all of K when you tensor with K. Okay, and now you just use the matrix multiplication like formula, like B of sigma tau is A of sigma B of tau plus B of sigma D of tau. So if you reduce mod I, the A's become chi's and the D's become chi2's, chi1 becomes chi2, and that looks really like a cocycle condition. In fact, if you multiply it by chi2 inverse of sigma tau, you get exactly the cocycle condition for that kappa. So now you've produced your kappa. Okay, and that gives you a cohomology class. And now the last thing to do is to prove that it's surjective, that it generates the B module. So this cocycle clearly generates the B module, right? Because it's just a scalar multiple of B, right? A unit multiple of B. And the B module is generated by the B's, so it's kind of obvious that it generates by definition, right? But you want to know that it's true for any cohomologous class. So let's assume I have a cohomologous class kappa prime. So the action is chi1, chi2 inverse. So to be cohomologous means I have this co-boundary, right? And now we can play some trick, which is you evaluate at sigma equals tau, right? And the point of sigma equals tau is that the kappa, which is a scalar multiple of the B element of the matrix, is 0 for tau, because tau, remember we made the basis lambda 1, 0, 0, lambda 2. So the B entry of tau is 0. So kappa of tau is 0. So I get 0 equals kappa prime tau, whatever that is, plus 1 minus chi1 chi2 inverse times x. Okay, but so now if kappa prime is valued in some proper submodule B prime, right? Then solving this back, so putting this to the other side, I get something in B prime, and this is a unit, so I'm using it for like the millionth time. This is a unit, so I can divide by it, and I get that x is in B prime. Now go back to the original equation. If this is in B prime and x is in B prime, then the sum is in B prime, so kappa is in B prime. So that means the original cocycle was in B prime, but I just got through telling you that the original cocycle generates B. So that's contradiction. All right, so that's the end of the proof of the residually distinguishable case. So now let me tell you the statement that we finally need and prove in to finish the proof of P equals 2 is Rivet's lemma and the residually indistinguishable case. So it's the exact same theorem. I haven't done anything except removed something, which is that chi1 is not congruent to chi2, not assumed to be not congruent to chi2. And maybe an important insight we had is actually what you can hope to prove in this context, okay? So we were trying for a long time to produce the module B, like a fractional ideal B, and look at something like B mod IB. And then at some point we realized that that's just not possible. Like you can't produce a module of the form B mod IB. And I think just realizing that was kind of a conceptual advance. Is that you just want to prove some module in a surjective cohomology class. Okay, but you need to know that it's big enough. So what is the property that you use about B mod IB when you end up proving this Iwasawa main conjecture, so these Brumer star conjectures? What you really use is that the fitting ideal B mod IB is contained in I. So then we said just put that, make that the condition you want, rather than forcing yourself to be able to form B mod IB. Just some module whose fitting ideal is contained in I. Okay, and so this is what we prove, and then the calculation. So the module and the cocycle are not that hard to write down, which is sort of the canonical thing you get out of this situation. Sorry, I forgot to correct this slide. I should have had the same assumptions as before. Instead of a continuous representation, which doesn't necessarily make sense, I should have said that the characteristic polynomials are continuous and that the image of the group ring valued homomorphism is finally generated. So I should have corrected that slide. The final point I wanted to make, I didn't maybe explain this. Why is this relevant for P equals 2 in the Brumer star conjecture? Why couldn't I use the residually indistinguishable case like I did for P odd. And why did we need to do all this work? Should have said this earlier. It's because you're making extensions of the trivial character by the characters that these odd characters, okay, that show up in the Brumer star conjecture. These are all odd characters. Everything's on the minus side. So you're an extension of the trivial character by an odd character. An odd character means that chi of complex conjugation is -1. So 1 is not congruent to -1 modulo a prime as long as the prime is not 2. So if p equals 2 is the only case where 1 is congruent to -1, and you need to have this residually distinguishable case of Ribot's lemma. And this was the difficulty why the Iwasawa main conjecture was open for p equals 2 for arbitrary totally real fields before our work, because Wiles had to make this residually indistinguishable assumption, so you can't do the Ribot's lemma aspect of the argument for p equals 2. So yeah, I could say that as the corollary of this work, and I'll talk about this more in my last talk. We get the Iwasawa main conjecture at p equals 2 for arbitrary totally real fields. It follows from this. All right. So I'll end there and just say that the details of the proof of this lemma, which I love, even though it's not stated right on the slide, will be given by Julia in her talk this afternoon. Thank you.